Hello everyone. So today we're going to talk about potential energy diagrams. And all this is a diagram that can be used to determine how the heat flows within a chemical reaction or some sort of process. So here's what we have. On the x-axis is just time, like the process of the reaction happening. So you've got the beginning of the reaction and then going through to the end of the reaction. And then if we look over here at the y-axis, you can see that we have energy in kilojoules. So this is how much energy it has. So if I look at my first question, it says products have blank energy than the reactants. So we're going to have the reactants on the left and the products over to the right, because you always start with your reactants and you're always going to end with your products. Okay, so we have products in this first example here have more energy. Sorry, I looked at the wrong thing. So products are right here. They have more energy than the reactants, which are right here. So what happens here is that energy is being gained by the system. And so if energy is going in, think about that word in, and is it exothermic or endothermic? And hopefully in your head you're thinking, okay, if energy goes in, you're thinking that reaction is endothermic. So let's talk about a couple things that we see happening in this graph. Some of the things that we can tell from this graph is that this right here is telling us the potential energy in the reactants. So remember, potential energy is how much energy is stored in the actual bonds. And so over here at the end, so these reactants have 100 kilojoules of potential energy. And over here at the end, we can see it looks like our products might have about 280-ish kilojoules of, again, this is how much potential energy is in those bonds. So now what is happening in this reaction is you've got the reactants, and in order to get a reaction going, we're going to need to input some energy, okay? So in order to get that chemical reaction going, we call this the activation energy. How much energy is needed in order to get the reaction happening? So we can actually calculate our activation energy, the amount of energy it needs in order for the reaction to take place. We can actually calculate that. So energy needed to have the reaction take place. So I can calculate it. Looks like we got to get up to about 380 kilojoules, but our reactants already started at 100. So 380 kilojoules minus that 100, we're going to have to add 280 kilojoules of energy. That's our activation energy for this guy. We can identify how much energy the activated complex has. So right here, I would call this activated. And we can identify that amount of energy right here. It's 380 kilojoules. That's how much energy we need in order to be activated. So we call that the activated complex. And then finally, we can also calculate our delta H by looking at this graph. Delta H is going to be the energy of the products minus the energy of the reactants. So for this particular problem, our products have, it looks like about 280 kilojoules of energy. Our reactants had about 100 kilojoules of energy. So our delta H would be 180 kilojoules of energy. That's how much energy in the end is going to be going in. Notice it's positive when I subtract my products minus the reactants. So let's look at another example. You can probably notice right away that this is the opposite of the other one. So we can see our reactants here. The potential energy of our reactants is about 400 kilojoules. Our potential energy of our products looks like it's about 100 kilojoules. We can calculate our activation energy. So how much energy does it take to get from the reactants to the products? So our activation energy, it looks like we got to get up to about maybe, I'm going to say about 480-ish kilojoules. And we're starting at 400. So 480 minus that 400, it looks like my activation energy is about 80 kilojoules. So my activated complex has 480 kilojoules of energy. So that is the energy of the activated complex. And then we can also determine our delta H of the reaction. So remember, delta H is the products minus the reactants. So if I look at my amount of energy of my products, I have 100 kilojoules of energy. My reactants only had 400. So my delta H, notice, is a negative this time. Negative 300 kilojoules for my delta H. So there's a few things we can notice is that the products, which are all the way down here, have less energy than our reactants this time. And so that means that energy is leaving, or energy flows out of the system. So hopefully when you're seeing those words out and leaving, you're thinking exiting, and so you're thinking exothermic for this reaction. And then notice, look, our delta H is negative, and we've seen already that when delta H is negative, it's exothermic. So that's what I have for you guys today, and you should go over everything we've done this week. Keep redoing all of the quizzes on Schoology, rewatch videos to review everything that we have done for this week, and make sure you've got everything done and completed to the best of your ability. And don't forget the Ed puzzle. It does review these potential energy diagrams as well.